When I was 16 years old, I had an after school job working for a florist. And one day, my boss had me go to a store that sold helium balloons. We didn't have a helium tank in our floral store, so I got into my boss's little car, and it was a hot summer's day, and I drove to the store that had the balloons. And when I walked into the store, it was one of those stores that when you walk in, it's like walking into a refrigerator. The air conditioning was so strong and it felt so cool in there. And it felt awesome because my boss's car didn't have air conditioning. So I was pretty hot by the time I got there to the balloon store. So I walked up to the teenager behind the counter and I asked for a dozen multicolored balloons. And she told me that she couldn't sell them to me because she didn't know how to blow them up. Well, I asked if I could blow them up because I knew how to work a helium tank. And she said, sure. So I went behind the counter and I blew up my dozen balloons, got them all tied up with their strings. And I walked out of the store. And then I had the problem of trying to get a dozen balloons into this tiny little car. Well, as I was stuffing the balloons into the car, all of a sudden, in horror, I heard pop, 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 pop. All but two of the balloons popped. I was humiliated because I had to go back into the store and ask to blow up some more balloons and pay for them. So, what did I do wrong? Well, the store was very, very cool, and walking out and putting those balloons into that hot car, gases expand with temperature. And if the pressure's kept the same and you just change the temperature, that volume will change. And so this is Charles' law. V1 over T1 equals V2 over T2. And so as our temperature goes up, our volume will go up also, and vice versa. So if we take our gas and cool it down, that would make the volume go down. So in Charles' law, the pressure stays the same. For example, a balloon, so an expandable container. And this is the same principle by which hot air balloons work. So in the lower left-hand picture, there is a man that's blowing up his hot air balloon. Notice that the balloon's basket is tilted on its side. So the first thing that they do is take their balloon and they lay it out on a tarp so that it can stay clean. And they usually have some sort of grassy park that they go to further keep things clean. And then they blow it up just with a normal fan. So they just take the air that's around the balloon and they'll blow it up. So just make it puffy a little bit. So this expands it enough so then they can take this torch and start heating the air that's inside. So as they heat the air inside, the density of the air in the balloon inside will be different than the density outside. And usually they do this on a very, very cold day or really, really early in the morning so that there is a greater difference in temperature inside the balloon and outside the balloon. So outside the balloon will be cold. Inside the balloon, as they heat it up, it will cause those gas molecules to hit the sides of the balloon with greater force and also hit more often. And so this causes the volume to expand. And eventually there's lift. So that basket all of a sudden will tip upright and the balloon will be above it. And then really, really quickly, the balloon is off. And on the right-hand side, it's really fun in the summertime. Certain places have these mass ascensions where you can see all these balloons being filled up at a park and they're launched at the same time. You get great pictures like this one here on the right. But they operate on the principle of Charles' law. As you increase the temperature, you'll increase the volume. And with those molecules moving faster inside the balloon, it creates lift because the density is less inside the balloon than outside the balloon. On the right here, we have a graph that has temperature at the bottom, and we see that as we lower the temperature, the volume is lowered also. And it has to do with those collisions because the kinetic energy is less, so there's less movement, there's less collisions, and so it causes that volume to drop. Notice that that red line stops at a certain point, and then you can extrapolate the line down to reach absolute zero, where theoretically the volume would be zero. Anytime you do gas law problems, the temperature must be in Kelvin. So please, please, please do not use degrees Celsius. You always want to be in Kelvin. And recall when you are calculating Kelvin, that Kelvin is equal to the degrees Celsius plus 273. So just because your temperature in a problem might be given to you in degrees Celsius, that doesn't mean that you use it. You always want to convert it to Kelvin. That way you avoid any negative numbers, because you can have negative degrees Celsius, but Kelvin will always be a positive number. So let's do one of your homework problems. So this should be question number 21, or a question that's very close to question 21. So look and try to match up that question. You can stop the tape and see if you can do the problem all by yourself, or you can just follow along with me. You want to identify all the units of the numbers. So the first number that we come to, this is a temperature number because it has Kelvin. So because it's my first temperature, this is my T1. And then this temperature has a volume of 100 liters. This is a volume unit, liters. And so I'm going to call it my V1 because it goes with the T1. So it says what volume, so I'm going to find a second volume, so that's what I'm trying to solve, if the pressure is constant and the temperature is increased. So here's my second temperature. So write your formula down. Again, this is Charles' law. And I want to solve for V2, and you don't have to do this step. You can just plug your numbers right into the formula. Just make sure that you follow the algebra rules. But I'm going to put V2 all by itself on one side of the equation. And I do that by multiplying both sides by T2. So I get V2 is equal to V1 over T1, and then I have a T2 on top. So let's solve for V2. So my V1 is 100 liters. My T2 is 350 Kelvin. And that is divided by my T1, which is 223 Kelvin. Notice that our Kelvin cancels, and then I can just do my math. So we have 100 times 350 divided by 223, and we get 157 liters is our unit that's left. And that is liters is a volume unit, so this works out. So this is your V2. So Charles' law, volume and temperature are directly related. So if your temperature goes down, your volume is going to go down too. If your temperature goes up, your volume is going to go up also.